Okay, thank you for Xiaomi's introduction, and also thank you for inviting me to give the talk here. And my talk is about non-local games with noisy. Maximally integral states are decidable, and this is joint work with my student Jimmy Long. Okay. Okay, I think the previous talk, the Zhengfeng already gave a very detailed introduction about these non-local games and interactive proof system. So I just quickly go through this brief this model. Okay, in the non-local games, there are two non-communicating players, player one and player two, and there's a third party referee. And referee is going to jointly sample a pair of questions, X, Y, under distribution mu, and send both X and Y to player one and player two respectively. And both players are supposed to reply a pair of answers A, B. And there is also a public predicate V, which input is X, Y, A, B, and output is 0 and 1, and 0 means lose and 1 means win. And we are interested in what is the highest probability that the players can win the game. Basically, they want the highest probability that they make the referee, or the predicate value is 1. Okay, and this non-local game actually captures many well-known computational optimization problems, such as 3-set. We know this we are supposed to given an instance of 3-set psi, which is a conjunction of a bunch of clauses, and each clause is a disjunction of 3 variables. So we can use these this instance to define such a game that the referee just draw a random clause uniformly psi I, and also draw a random variable occurring in this psi I, and then send the clause to the player one and then send the variable to the player two. And the player one is supposed to reply assignment to all variables to this clause in this clause, and the player two is supposed to reply assignment to this variable. And we say that the player wins the game if the assignment received from player one should satisfy this clause, and the player one and player two, because they assign the value to a same variable, so they should assign same value. So the assignment should be consistent. And now you can see if psi is satisfiable, of course, the players can definitely they can just choose a satisfied assignment, so they can win the game with probability 1. If it is unsatisfiable, then no matter what strategy they use, anyway, that what assignment they choose, that at least one clause which is unsatisfied. So the highest probability they win the game is at the most 1 minus 1 over 3, and M is a number of clauses. So we can see that, so basically it captures a set problem. So you can see, so of course, the computing the value of the game is NP hard. Now, but we can we see that actually first set is satisfiable, then you win the game with probability 1. If it's unsatisfiable, then win the game with probably less than 1 minus 1 over 3, which is, so there's a gap, which is 1 over poly to the size. So basically, we can further strengthen our result that approximating this value of game to a 1 over poly precision is also NPR. And thanks to the famous PCP theorem, now it is known that even approximating this value of game to a constant precision is also NPR. So so yes, now we are in a quantum conference. So of course we are interested in entangled quantum games, or sometimes called entangled non-local games. This actually is in the previous talk, Zhengfeng also introduced model. So the model, everything is almost same as the previous. So they're classical non-local games. The only difference is that now the players are allowed to share the arbitrary bipartite entangled states. So of course, in the classical, you can also assume, in the classical game, you can also assume the players share classical streams, but you can prove that the sharing classical randomness is useless. So okay, now we can also interested in the value of this quantum game. So now you also need to maximize over all possible share entanglement between the players. But since we do not give an upper bound on the dimension of the share entanglement, so this make the computing the value of this game is much more difficult. So of course, so now the question is, what is the complexity of computing this quantum value of this game? Okay, and this also was mentioned in the previous talk, as there was this quantum game that's a motivation from physics, because there's a famous game called the CHSH game, whose classical value is 3/4, but quantum value is strictly bigger. So, and this was equivalent to the well-known space inequality, which revealed this Einstein's famous words. Okay, so there's a lot of related work studying the hardness of how to compute this omega star G. This also is, I also mentioned in the previous talk. So here I just give a very partial list. So there are some games which are easy. So for example, the Cliff et al. Prove that entanglement SO games are easy. Here being easy means that it exists a polynomial time algorithm. And later, the result was strengthened by Kempe et al. Show that entangled unit games are also a polynomial time algorithm. And both of algorithms are using semi-definite programming. So, and interestingly, actually both of these games in the classical setting are proved to be NP-hard. And on the other side, of course, there are many hardness about the computing value of these quantum games. Here we just emphasize the last one, basically just in the previous talk, the G, they prove that actually approximating this value of the game to a constant precision is RE completely. So basically it's as hard as deciding holding problems. So, and further it shows that they prove that even if the players are only sharing EPR states, and the game is still NP-hard. But originally the game, we allow the game players share arbitrary entangled state. But in that proof, actually, they show even you only allow the players share EPR state, it is only as hard as you sharing arbitrary quantum state. Of course, you should have infinitely many copies of EPR state. Okay, and now in this talk, we consider another aspect studying the non-local games, because we are thinking, is it possible, possibility to implement such games? Okay, we know that of course it will not happen in the real life, because the game the players should share infinitely many EPR states. But this sort of implies that if the players share more and more EPR states, the game should be more and more powerful in some sense. But on the other hand, we also should consider that in the real world scenario, the noise is, we know that noise is completely unavoidable when you're really implementing any quantum computing. So in this talk, we are interested to get what happens if the non-local games are suffering some noise. So, okay, but the noise can be happen everywhere. So let's first consider simply what happened. The noise happened between the communication between the players and the referee. But because the players and referee basically they're just exchanging classical messaging, so we can just use a standard error correcting code and which eliminate the noise. Okay, so that is, so noise happening in those messages is not an issue at all. So what happens if a noise is happening between the players? Basically, basically the shared state between the players are suffering some noise. So, okay, maybe your immediate thought is that this probably is also not an issue because we have a rich theory about quantum error correcting code. So maybe you can adapt some quantum error correcting code to correct those errors and make the game as hard as like perfect. So we take a step to study this question, and we consider a very simple noise, probably also one of the most natural noise in quantum information theory, is that it's called depolarizing noise. So what if the players now sharing noisy EPR states? This is each EPR state, but each EPR state with probability epsilon, it will be replaced by a complete mixed state. This is the white noise. And of course, now I was interested now what is the highest probability they win the players win the game if they now share infinitely many noisy EPR states. Of course, now here's some remarks. So first, the GA does will basically prove that if the noise is 0, then this game is undecidable. Basically, computing this value to a constant precision is undecidable. And the second is that we know that this noisy EPR state is entangled if this noise is really small. So if the players share more and more noisy EPR state, then the entanglement between the players should also tends to infinity. So in some sense, they can make use of, may be able to make use of this unbounded amount of entanglement to make the game hard. So another one we can also be asking, okay, are the strategies for non-local games are really robust against the noise from the shared state? And actually the answer is no. This is our main result. We prove that if the players are sharing noisy EPR states, then we can give an upper bound on the shared state, the copy of EPR state, noisy EPR state for the players to achieve the value of game to arbitrary precision. So since now we have upper bound on shared state, then you can just brute forcefully enumerate all possible strategies. And the number of copies is exponential in the size of question answers and double exponential to the 1 over the noise and 1 over delta. So that means, okay, if your noise really goes to 0, the number of copies should go to infinity. And okay, and here's a remark that all the previous algorithm for the value of game G for some special class of G, like what we mentioned, the unit game, XOR game before, they're all via convex optimizations. And but in this work, we are using a completely different approach. We are trying to simulate a high entangled strategy by low entangled strategy. And actually, we even strengthen our results, showing that what happens if the players are allowing to share high dimensional EPR state, which we sometimes also called the maximally entangled state, which is it's like m dimensional EPR state. And yeah, you can, as long as the dimension is bounded for each maximally entangled state, you can still give upper bound, and then you should pay for another exponential log m here. Okay, so now let's go to the high-level proofs. So basically, in this work, we are answering a more basic question that if the players are sharing infinitely many copies of noisy EPR states, what classical distribution can they sample without communication? Basically, the player one player just do some local operation and output some distribution. What distribution can they sample? So before answering this question, let's even take a further step back, asking the classical analog of this question. Say now the players are sharing infinitely many copies of a classical distribution, say P, which is a bipartite distribution. And we still, without communication, what distribution can they jointly sample? And this problem was called the non-interest simulation of joint distribution. It has a pretty long history. It looks back to 1970s. And surprisingly, until very recently, like 2013, 2014, the decidability of this problem was resolved by a series of work. Here, decidability means that means that exists n such that if a player shares n copies of P, they are able to sample a distribution Q prime, which is absolutely close to Q. No means for any n, no matter how many copies the player share, whatever distribution they jointly sample Q prime will be 2 epsilon far from Q. And the proof was built on a very rich theory called theory of analysis of Boolean functions, which is nowadays a very powerful method in computer science, theoretical computer science. For people, if you are interested, I highly recommend this excellent textbook by Ryan O'Donnell. Okay. So now let's go to the quantum case. So first, of course, this problem has a very natural quantum analog. That if a player share infinitely many copies of bipartite quantum state rho, what question without communication, what quantum state sigma can they jointly create? And this problem was, some people call it local state transformation. And as far as I know, it was first studied by Beijing. And he gave a necessary condition for the players to share one copy of rho and create sigma exactly. And other than that, there's not much other further research. So in this talk, actually, we prove that this actually is decidable if the players share, if they share noisy EPR states, and the target distribution is a classical distribution. And our work basically just try to quantize this previous work by Decidabl. So we really need to generalize the Boolean analysis to Hermitian operators and the random operators. Okay, now let's go to get further details of our proofs. So the question, so let's say, so first now at least the players share many copies of noisy EPR states, and the players strategy. Okay, this is player one and player two strategy. Basically, they are just performing POVM, P1 to P and Q1 to QB. Our goal is to construct another pair of POVM acting on a smaller Hilbert space, say D dimension. Initially, we have n dimension, n is unbounded. Now we only act on a bounded dimension, D dimensional. And the player one strategy now is P1 prime to PA prime, and the player two is PQ1 prime to QB prime. And this construction should meet several requirements. First, this D, the bound copy of EPR should be a universal constant. Should be independent of everything. And for any n, first, the POVM, new POVM you construct, it should be a POVM. So being a POVM means each operator, PI prime and PQJ prime, it must be positive semi-definite. And second is in PO means the summation of PI prime should be identity. Summation QJ prime should also be identity. And now third requirement, we won't say that both strategies should output the same distribution. So meaning that the probability they output, at least output, player one output I, player two output J, should be close in both scenarios. So for the first case, it should be something like this, right? Probably trace PI tensor QJ acting on n copies of psi. And this new strategy basically PI prime, QJ prime acting on B copies of psi. And last requirement is that because we are working on non-local games, so players may perform different measurement depending on different questions. So we want this construction should only depends on the local information. So meaning that player one when you get from P to P prime, he doesn't need to know what happened to Q. So Pi prime should only depends on Pi, and Qj prime should only depends on Qj. Okay, so as I said, now we want to get generalize the Boolean analysis to Hermitian operators. So Boolean analysis basically is just Fourier analysis on over Boolean functions. And Fourier analysis is a simplest way to explain. Basically, you choose you define it in the product and choose an orthonormal basis and write everything in a linear combination of this basis, and everything is done. So we do the same thing. We need to choose a basis for operators, basically just matrices. So we know, and so here's a very natural choice. If you are working on 2x2 matrices, it's a poly basis. And if any 2x2 matrix can be written as a linear combination of all these poly bases, and we know that it is Hermitian operators, then all these coefficients are real. Now, if we are working on n copies of an operator acting on n bits, then the base you just tensor product n poly matrices, and it will form a poly basis. You will form a orthonormal basis in M2 tensor n. Okay, then now we consider this. Okay, now we consider this P is the Fourier expansion of P over this poly basis, and this has a very it also has many properties, same property as in the classical Fourier analysis, such as we also have Parseval identity. And here let me first introduce something called normalized P norm, which is basically almost same as the Shelton P norm. Only difference that you need to normalize to the dimension before taking to the power of 1 over P. Okay, so the difference of this normalized P norm from the Shelton P norm is that for Shelton P norm, we know that it is monotone decreasing with respect to P. So it's like 1 norm greater than 2 norm, greater than 3 norm, greater than 4 norm. And normalized P norm is like a reverse order. So it's like 1 norm, less than 2 norm, less than 3 norm. Okay, now let me go to how do we construct P prime and Q prime from PQ. So suppose now players are performing operation P on the P. So let P to be one of the POV element in. So first step we apply the smoothing operator, because smooth operators by applying the noise operators T low, which is also this noise operator is this term usually used in Boolean analysis, but in quantum information community, people also call it the depricing channels. So you apply this depricing channel to every coordinate. So we know initially the P, which is Fourier expansion of P, and we know that depricing noise basically it maps identity to identity. And for other poly operator, you just multiply by a factor rho. So when you apply a deprive noise, so you basically for sigma s, you just multiply by the rho to the absolute of s. Here absolute s basically is a non-zero entries or number of non-zero entries in s. So now you can split this P1 to 2 parts. One part is the part that which this non-zero entries of S is small, and another part is the non-zero entries is large. And we know that if the S contains many non-zero entries, then you're going to multiply by a much smaller factor. So if you choose D pretty large, then this weight of this high degree part will decrease exponentially. Okay, now then second step, we're going to introduce another concept, which also very common in Boolean analysis, which is called inference. The inference of a coordinate is defined in this way. Basically, you just trace out that coordinates and replace it by identity over 2 and measure the difference with respect to the L2 distance. And you can prove that the total difference, so that summation of all coordinates influence will be upper bounded by the degree of P. And because of step 1, now we know that this P is already low degree, high degree part can be removed because it's exponentially small, so you can remove it. So the summation of all coordinates influence is now bounded. And so that means the number of high influential coordinates is bounded. Okay, so now we can split to this P1 to low influential coordinates and high influential coordinates. And we know these high influential coordinates are bounded. And the next step, we're going to do substitute all these low influential coordinates by Gaussian variables. What should we do that? We're going to basically just for each coordinate. Okay, for each coordinate, we just introduce three independent Gaussian variables. And basically, we just replace sigma 0. Because we know that sigma 0 is identity. We replace sigma 0 by 1. And if it's sigma 1, sigma 2, sigma 3, then you just replace by 3 independent Gaussian variables. Now you get the random operators, which is a bounded dimensional, but now the coefficients are random variables. So you can rewrite these poly operators, and now it is. So you can see that now coefficient is a function of Gaussian variables, and you can verify that basically all these functions are actually low degree polynomials. Okay, and the next step we apply a dimension reduction for low degree polynomials of Gaussian space, which actually was not proved by Ghazi around 2016. So now then we get a new operator which now have a bounded number of Gaussian variables. Okay, now we get the operator which have bounded number of Gaussian variables and a bounded number of poly operators. And further we need, then next time we use some actual work, we're gonna do further substitute the Gaussian variables by metric basis. And then because now you only have bounded number of Gaussian variables, so you get a bounded dimensional POV element. So this is the whole construction of work. First, we apply the smoothing operator to make the operator to be low degree, and then you identify a bounded number of high influential coordinates, and you further replace all low influential coordinates by Gaussian variables, and you further apply dimension reduction to reduce the number of Gaussian variables, and still keeping the number of poly operators unchanged. And then further replace the Gaussian variables by poly operators, and in the end you get a bounded dimensional POVM. And actually only the first step. So maybe ask, where do we use the fact that the players share noisy PR states? And actually the noise is only required when you do the first step, when you apply the smoothing operator. Okay. So here's, let me further, give one more slide to summarize the construction. We have this first step, each step, this is our objectives. First step, loading. And here's some remark that actually the step 1 and step 4 are unital and linear. Unital means they change identity to identity. And linear, basically, this map is a linear map. Okay. And step 3 and step 5, we need some extra massage, which we call the rounding, which I'm going to explain later. And because of rounding, so these step 3 and step 5 are both nonlinear. Because it's nonlinear, so we also need to say, okay, we need to say this construction should meet all the requirements. So these two steps are most complicated part. We need to introduce a quantum invariance principle and quantum hyperconjective inequality. Okay, so let me get to do this step 3. Okay, and step 5 are same. Then let me remind what we do in the replacement. So we have a poly operators. We have a POV regular POVM, and we do such a substitution. We just replace for every coordinate with sigma 0, you replace by 1. Sigma 1, sigma 2, sigma 3 is just replaced by 3 independent Gaussian variables. So here you have a totally n minus h coordinates. So basically you introduce 3 n minus h independent Gaussian variables and perform this substitution. And now you get a random operator. Then let's recall what the requirement we need to meet. We need to ensure first it is still POVM, and probably output the IJ should be same after doing the transformation. Good. But because because we are now, it is P and Q are random operators. So of course you need to take into account this randomness. So you change this. So you can, this item 3 should be replaced by the expectation over the randomness, internal randomness of this PQ. And it's not hard to verify that the steps, item 2, 3, 4 satisfied easily. So only issue is step 1, because now that we have a random operators and because also Gaussian variables are unbounded. So with high probability, these random operators are not positive symmetry. So instead of proving the positive, we're proving that the expectation of the distance of this random operator to a PSD matrix, positive PSD matrix, is close to 0. So this is what we use a quantum invariance principle. Basically, if we have, we prove that if we get a plane P2 in this way, then the expectation of P2 and the PSD matrices, this normalized 2 norm square is upper bounded. Okay, now let's go to how to prove it. Okay, here's a recall what do we do the substitute. Basically, you just replace all the Pauli operators in low inferential coordinates by Gaussian variables. And here we multiply sigma 0, which is identity of such make these 2 operators are of the same dimension. Okay, so now let's see. We want to prove that an operator is close to a PSD matrix. So given a Hermitian operator, the closest PSD matrix can be just simply obtained by replace all its negative eigenvalues by 0 and keep high non-negative eigenvalues unchanged. So basically we just apply, if you apply this function Rx to this P, you're going to get it is closest positive symmetric matrix. So essentially we want to prove that if P is a PSD, Rp is P, then R random P is close to random P. And let's further rewrite this function, the distance of x minus x. So you can easily see the function looks like this. So okay, equivalently we can say this. We want to say if we trace this zeta, this function zeta acting on P is 0, then expectation of trace zeta random P is also close to 0. Okay, so here's the main technical part. We are going to apply the hybrid argument, which is which of course is used many places in computer science, and in probability theory, people also call it the Lindenberg argument. So we know that from P to random P, you're going to replace all the Pauli operators in low inferential coordinates by Gaussian. So hybrid argument, we just do it step by step. So Pi, we're gonna just replace H plus I coordinate because we are starting from H plus 1. And then we know that from Pi, we know here we got sigma 0, we're gonna just replace by 1. So from Pi to Pi plus 1, they share a term in common. Basically, the Pi plus the common term is the part that ith coordinate is sigma 0. So which we write it as a Q. So Q is H plus I plus 1, coordinate is sigma 0. And of course, they have a different terms, which is Ri. So we know now, you see the pi base is q plus I, and pi plus 1 is q plus I plus 1. And we starting for this hybrid argument, we start from p and ends with random p. Okay. And we can prove that the expectation of the two normal Ri square, which actually is the influence, as coordinates influence of p. And as we already said that after doing this smooth operation, all coordinates we're going to replace are low influential coordinates. So meaning that the norm of this Ri is small. So now you can see that basically pi and pi plus 1 are pretty close to q, right? So we want to say we want to try to argue that trace zeta pi is close to trace zeta pi plus 1 because pi and pi plus 1 are very close to q. So a natural choice, we just use a Taylor expansion of this function at q. But the bad news is that this zeta is C1. Basically, it only has it also has first order derivative. The second order derivative only exists except for finite point. So it's not that smooth enough. So doing that, we avoid that. We're going to introduce a smooth approximation of zeta, which is C2, and the approximation looks like it is quite complicated. Anyway, you can just do it by hand. It's not that hard to get it. Okay, good. Now Okay, now we said now we want to apply to Taylor expansion of zeta lambda at q, zeta lambda pi at q. So we just do this. Because now the function we are working here is a function acting on operators. So the input is operators, output is real numbers. So here we use something called the Flesch derivatives, which is a generalization of derivatives in Banach space. Yeah, then you can do that. You can, because of the non-commutativity, so the Taylor expansion, the derivatives. Computed derivative is much more involved. And of course you Taylor expanding both pi and pi plus 1 at q. Okay. And next time you can argue that both this first order and second order are same. So only difference is the third order term. So third order, you can upper bound it. The third order is actually the expectation of normalized 3 norm cube of I. So because now we're starting from P0 until PH, also P-H, so in the end, and we know trace zeta P is 0, so then you just summing all the difference for each hybrid. So in the end, the trace expectation of trace zeta random p will be upper bounded by this term. But as we said that the normalized 2 norm of Ri is influence of p, which is small. And we also said this normalized p norm is increasing with respect to p. So we cannot use this 2 norm to upper bound the 3 norm. To avoid this issue, we need another called the corner hypercontractor inequality, which says if an operator is low degree, then this normalized 3 norm and normalized 2 norm are almost same up to this power degree. So you need to pay for the factor of 3 of degree. And we know that because R is a part of P, and because of this, first time we do the smoothing operator, so we already make the operators low degree. So good. That's good. So we can replace that 3 norm by reduce 3 norm by 2 norm, pay for 3 to the d. And we know that 2 norm square is influence. So you got the summation I influence p to 3 halves. And of course you can make this simple trick. And because now we know that for each coordinate, the influence for each coordinate, the influence is small. So this is small, and we also set the total influence of, or summation of all coordinates influence upper bounded by D. So in the end, this trace P2 is going to be bounded by this, and which we can do is small. So this is our whole construction of transformation, and okay, and here's some further direction and open problems. First, here we prove that the player share noisy EPR states are undecidable. Undecidable basically means that non-local games are not robust against the noise from the share state. But what happens if the players share any given state role? Any given state role, but the players share infinitely many copies. Are they for what role they are decidable, for what role they are undecidable? But now we know that for EPR state it is undecidable, for noisy is. So for EPR is undecidable, for noisy EPR is decidable. And then can you do this classification? And our conjecture is that if the state role are noisy, basically it's any state you just put some depressing noise, then the game will be decidable. But yeah, we don't know how to prove it. And we can further ask question: what happened? What the decidability of local state transformation? Basically, if players are sharing infinitely many copies of state role, can they, and a given sigma, can they generate sigma via local operation? And also, this can also, we can also ask what are non-local games with quantum questions and quantum predicates. And there's some further questions because the invariance principle is a very powerful method in classical TCS. It has been used in many areas, and nowadays the proof of classical invariance principle is very elegant and also very general. But here we only prove a very special case. Just basically we just prove for that specific function we have a quantum invariance principle. And can we have a more general version of quantum invariance principle? And the second is actually this framework give a framework to study the computability of these tensor quantities. Basically, you have n copies of some quantum state, and n goes to infinity, and how it behaves. And we know that in quantum information theory, there are many such kind of quantities, such as quantum channel capacities, and various regularized in quantum entangled measures, quantum information complexity, etc. And all these quantities now we don't know how to compute. We don't know whether they are computable. And we hope this framework can give a new approach to study these questions. And the last is, we said the application of Boolean analysis in quantum information theory is still not as rich as in the classical setting, so we'll be very interested to see more applications. Thank you.
Thanks, Penghui, for the wonderful talk. I have a few technical questions.
Yeah.
So as you list in the open problem for the quantum invariance principle, so are there any other potential application for this invariance principle?
Yes. Definitely. Because all this invariance principle of free analysis, there's an underlying distribution. And right now we are working on noisy EPR state because the marginal is uniform distribution. Yeah. And for this and the free analysis, everything are pretty good. The performance is pretty good. So if you are able to prove a quantum invariance principle under arbitrary distribution, then you can prove that if the players share non-EPR state, other quantum states, maybe the marginal are not uniform distribution, I think you can still prove this ability. And even you can also, basically that. And I think if you want to study this, such as this quantum channel capacity entangled measure, you really have to get the general invariance principle.
Okay. Then my next question is, will this be all other techniques in your construction be used for the quantum error correcting?
Quantum,
or even in the quantum distributed computing?
Oh, yeah, I think the Fourier analysis was used in some such as in quantum communication complexity. There's many problems lower bounds are using Fourier analysis, but all those applications more like it's pretty ad hoc. Basically, it's designed for that specific question. And for example, just today's archive, there was a paper about yesterday. It's a correlation. I think they also used some
okay.
Fourier analysis.
Yeah. Mm-hmm. I see. Okay. So I see a problem from the Bilibili. He asked whether this can extend to multiplayer.
Oh, that's a good question. And I think it will be very difficult for this problem, even for classical non-interactive simulation, for three parties is now completely unknown. So, because the constructions, you can see, the construction, okay. Basically, the construction, the first step is already fails when you do the smoothing. So yeah, and I think it'll be very interesting if you can even get three party is already, even in classical setting, three party is already very challenging.
Yeah. So actually, I have another question. So actually, in the non-local game, there's the referee, but however, it seems you change to a two-player cooperate to generate some distribution. There's no the referee. I wonder, well, will this be the same in the multi-party?
Oh yeah, yes, of course. For the non-local games, yeah, because I think we already know that for non-local, even quantum non-local games, two players already RE. You see, so there's no strong motivation to go to three party or four party. But what I'm talking about is non-interactive simulation. Say players share a three-party distribution. And other questions, if they have infinitely many copies, now what classical distribution can they jointly sample?
Yeah.
And and this in classical we don't know. And of course we can also ask for even quantum non-local game for three-party or four-party. If the share space are noisy, are they still decidable? That we don't know.
Okay. Okay. Are there any other questions from the room? Okay. If not, let's thank Penghui for the nice talk. Thanks. Start at 2 p.m. Okay.